Hello folks, and today we are here with the starting of the one shot video, detailed explanation video of the CBSE class 11, Computer Science, chapter 3, number systems and encoding schemes. We'll be covering, we know, these are the table of contents for today. The introduction to number systems will be covering decimal number system, binary number system, octal number system, hexadecimal number system, how to do the conversion from decimal to binary, octal, hexadecimal with fractions also, from other number system like binary, octal and hexadecimal to decimal with fractions also will be learning. Conversions between binary, octal and hexadecimal. Total 12 types of conversions are there that we saw in the previous introductory video. So check out the video if you didn't know what is the content for today. That gives a precise content of what we'll be learning today. The encoding schemes we'll be learning in ASCII, ISCII and Unicode here. Some quick revision notes, some more exam questions, common mistakes that we should not make, and chapter summary will be taking over this today's lesson. Yeah, let's start the lesson today. And first, let's understand what is a number system. Number system is something. It is a systematic method of representing numbers using a consistent set of symbols or digits that we have, right? So every number system has a base that is also known as a radix. It tells us how many unique symbols are there. Like in the binary number system, that is of the base 2 because it uses the digits only 0 and 1 that we know it. Likewise, in the decimal number system that we know, the decimal number system is of the base 9. It uses the digits, sorry, base 10. It uses the digits from 0 to 9. The total digits are 10 that we know this. The computers are digital machines, we know. They operate in the electronic signals that are either in on state, true or 1, or in off state, that is a false or 0. So because of this physical limitation, computers use the machine language and the binary number system at the hardware level. However, the humans are more comfortable with decimal number system, and programmers often use octal and hexadecimal as convenient shorthand for binary. So things like 10 can be represented in many ways in different systems. In decimal, we write at 10. Octal it is 12. In binary, it is 1010. In hexadecimal, it is 10. So all they represent the same quantity, but written as differently to take care of this. So these are the base of the four number systems. Binaries are base 2 as it and in two digits only 0 and 1. Octal is of the base 8 as it consists of digits from 0 to 7. Hexadecimal is of the base 10 that is consisted is from 0 to 9. Hexadecimal is of base 16 that is consisted of 0 to 9 and A to F that we know. So all four systems are positional. It means the value of the each digit depends on two things. The digit itself, that is a face value, and its position in the number we determines its place value. So basically this is a formula. So this formula is not that much required. So we're moving directly to a decimal number system. Decimal we know, daily number system, it is consists from 0 to 9. There are 10 digits and its bases respectively 10. And basically we need to express 534 in positional notation. How will you represent this? 5 is in the 100 place, 3 is in the tens place, and 4 is in the ones place. So we represent this notation in form of 534, that is 5 into 10 square plus 3 into 1 to the power 1 and 4 into 10 to the power 0. That is 5 into 100 is 500, 3 into 10 is 30, or 4 into 10 to the power 0 means 4 into 1 basically. Anything to the power 0 is 1, na? It's 4. So to calculate this whole thing was 534. That we represent. And if the question is there to express 122.238, this is a number with some fractional part. Number with some fractional part. This is only a normal int number, but this has fractional or the float part that we discussed, right? So in positional notation, how to represent this? 123.238, 1 into 10 to the power 2 plus 2 into 10 to the power 1 plus 3 into 10 to the power 0, and in the decimals we go the reverse way, plus 2 into 10 to the power minus 1 plus 3 into 10 to the power minus 2 plus 8 into 10 to the power minus 3, and the decimal point separates the integer part, the positive powers of the base, from the fractional part of the float part, that is the negative power of the base. This rules apply to all the number systems. Just remember this key point. Then we go ahead to the binary number system. In binary number system, there's an on state, there's an off state. So it has 0, there's a 1. It means low voltage, no signal. It represents high voltage, a signal is present. Our computer hardware, transistors, logic gates, all were these two electrical states they have, on and off, true or false, yes or no, right? So important terms we will learn here. Binary digit may be represented in the previous chapter by any uppercase letter, and there may be a most significant bit, that is the leftmost bit, we say, right? Bit is the highest value, and the least significant bit, that is the rightmost bit, the lowest value. Bit is the lowest value. To remember these terms, let's say we have a number that is a 138. In this 138, 1 is a MSB, most significant bit, because 100 is of the greater value in the 100 place, and 8 is in the units of ones place. So it's the least significant bit, right? So we can discuss. And if there are like two numbers, if 28, so this 28, this is in 10th place, so this is the MSB, and 8 is a NSB here, least significant between 28. And let's say if we have just one number, let's say 1, so 1 is itself the NSB also, and 1 is itself the MSB also, most significant, least significant, because there is only one digit, unit digit is there. So binary number positional breakdown you can do, जैसे कि 101.01. So first is, let's say, in 2 square form, other is 2 to the power 1, other 2 to the power 0, point is in point, this is 2 to the power minus 1, and 2 to the power square inverse, it is there. And then you just calculate the value. 1 into 2 square is 4, then 0 into 2 is 0, 1 into 1 is like 1 here, and here like 0 into inverse, 2 inverses 0.50, and 2 square inverses 1 into 0.25, that is 0.25. Add it 4 here, 0 here, 1 here, 0 here, and 0.25 here. It becomes this 5.25 base 10. If you convert in decimal, binary to decimal conversion is happening here. This you have to understand this. Later we'll be discussing that. Then maximum values is n bits. Combinations: 1 bit, 2 to the power 1, 2. I discussed this in the number of rows when we're discussing this Boolean logic, the n, 2 to the power n. This formula we discussed, right? 2 to the power n. There will be 4 rows in 2 tables. Voila. The same formula is like here. You have to discuss the range 2, 0 to 3, 3 2 cube 8 to 0 to 7, something like that. Then we proceed here to the octal number system. In octal number system, it has a base of 8 and uses the digits from 0 to 7, basically. So in each octal digit corresponds to 3 binary bits, right? So these are the thing, 3 binary bits and 3 binary. You can see here, let's say, uh, 0 is written as 000, 1 is 001, 2 is 010, 3 is 011. You have to remember this. 4 is 100, 5 is 101, 6 is 110, 7 is 111. You fill this like this, and this is equivalent table. Okay. An octal positional notation. Let's say convert 536.67. This is an octal here to decimal form, positional notation. So how do we convert it? This thing, 5 into 8 square plus 3 into 8 to the power 1. 2 into 8 to the power 0, 6 into 8 to the power minus 1, 7 into 8 to the power 8 square inverse it is, right? And then you do 5 into 64, 3 into 8, 2 into 1, 6 into 0.125, but this is like 1 only, and so it's 1 here, and 7 into 0.15625. You mean your calculator do this, add up this value, and at the end this you get. This is the conversion happening, that the base is 8, so you're multiplying 8, because you're converting to octal to decimal, and here from binary to decimal, base is 2, so you're multiplying by 2. So remember this when learning this ahead, take note of these things. But what are the uses of this octal? That is the main thing. File permission codes is used in Linux and Unix system like chmod 755. Representation of UTF-8 encoding numbers will be seen in Unicode, and systems where word length is a multiple of 3 bits. Oct, you can think of an octobus or october, that is 8 month, usually not 8 month actually, it's actually like 10 kind of thing, but yeah, octobus you can relate with. So you can remember the word like it consists base 8, so 0 to 7, and octobus are 8 arms I have. Hexadecimal is base 16. So how this hexadecimal works, it is 0 to 9 and A to F. It means that A is represented at 10 and this is 15 F, and between like 11, 12, B, C, all this represented like this, and each hex digit maps to 4 binary bits. In octal there were 3 binary bits, but here there are 4 binary bits. This 2 to the power 4 is 16. So that 2 to the power n formula is working here. And how to represent 0 as 4 zeros? 1 is 0001, 2 is 0010, 3 is 0011, 4 is 0100, 5 is 0101, 6 is 010, 110. 7 is 0111 like this, and this is hexadecimal, decimal format, 4-bit binary, hexadecimal part. So you have to understand this table and remember this some of the things. Basically you can see all these are 3 are same, in front 0 is added with this, compare, just 0 is added in front everywhere. It is the same thing. The main changes given: A, that is 10, B is 11, C is 12, D is 13, E is 14, F is 15. All biocodes die eventually forever. Hex letters is simply from A to F. This is just mnemonic, it's not even required. What are the real world uses of hexadecimal then? Memory addresses, like 16-bit memory addresses. Web colors in CSS fonts or something if you have done. It is like this. MAC addresses, hardware IDs, error codes. So these are the uses of hexadecimal. Then we go to conversion part basically. From decimal conversion to octal, binary, hexadecimal. How to do this? Remember this rule. Repeatedly divided by the target base. Read the reminders from bottom to top. Last remainder is equal to the MSB, most significant bit, for the integer part. For the fractional part, repeatedly multiply the fractional part by the target base. Read the integers first from top to bottom. Stop when fraction equal to 0. Sufficient precision is reached. So this is an example how to convert 75 with the base 10 when 75 is in decimal to binary format. How to convert this? You do 75 here, or let's again start from here. 75 you repeatedly divided the base 2 with which you want to convert. Binary is base 2, so divide by 2. It will give you 37. 1 will be the reminder here, you're writing the reminder. Divide by 2, 18. 1 will the reminder. 2, 9, 0 is a reminder. Then 2, that is 4. Let me move, sorry, yeah. So as you can see this thing here also, 75 divided by 2 is 37, remainder is 1, divided by 2, 18 you get. remainder 1, 2 9 remainder 0, 2 that is you get 4 remainder 1, and 2 you get 2 remainder 0, and 2 when divided by 2 you get 1 remainder 0, and last you get 1, right? So 1 is a MSB, or the most significant digit bit which what you go. Then you basically go from top to bottom. Top to bottom if you go, what is basically there? 1 0 0 1 0 1 1, right? So if you understand this thing, so yeah, so this is a result. If you go this, 1 is the last we saw, the 1 0 0 1 0 1 1. This gets in from decimal to binary conversion, very easy. This is with the decimal numbers. If we do it with the, let's say with our fractional part or float part is there in the numbers, like 142.67 to binary fractional part, what will be doing first with the integer part will be taking 142, you divide this with 2, you get 71, remainder as 0, and divide with 2, it's 35, remainder is 1, go and divide it 2, 17, remainder is 1, go divide by 2, remainder is 1, go divide by 2, you get 4, then you get 2 here finally, and here you get 2, then you divide by 2, you get 1. So basically this will be getting, if you see all the formats, right? uh, yeah, so if you get this, you'll do the same thing for this integer part. 1 will be the most significant bit, 0 will be least significant bit. You write this 1 0 0 0, you'll be getting 1 1 1 0, and this is the binary part for this 142. But how to do is a 0.67 part. Now for that we'll be moving here 0.67, and we're converting into binary. You multiply by 2, 1.34, right? 1.34 you got, then you got 0.34 into 2, 0.68, you left with 1 here, you left with 0 here, 0.68 that we got into 2, 1.36, you got 1 here, and 0.36 into 2, 0.72, you get as 0, right? Read top to bottom, you need to do the 0.1010, you need to add it. That's a fractional part, right? What we basically did is to convert. Try to understand the logic of this. You get 1 somewhere, multiplying by 2, you get this 1 part, 0.34 remaining, multiply by 2, 0.68, 0 remains, 68 pura you bring it here, the whole thing, into 2, 1.36, brought 1, 0.36 into 2, 0.72, 0, that is 72 remains, 1010 you need to have it. So basically like this, that is the conversion part that we need to understand. And or there previously also we saw this, how to convert this part, binary with positional breakdown. There were 2 square, 2 to the power and 2 to the power 0, this is -1 -2, it was there. So if you do positional breakdown like that, that will also be coming the same, and this is one method to do it. And decimal to octal, how to do it? Just like this, 104 you do divide by 8, you get 0 remainder 13, divide by 8, 5 remainder you get 1, 8 remainder 0, you get most significant bit is 1, 150, you again go from bottom to top and you get 150. So this is easy, you have to understand this part, how it is calculated. uh, and yeah, same thing for the integer 563. You will do this 0.93 simply multiply by 8, 7.4 remain 4 into 8 something, you remain this, bring the rest part, do this, and again this, do this, repeat 4 times, only 4 times you need to repeat it here, not more than 4 times, 4 times. Remember here also, yeah, don't get confused how many times you need to repeat. You need to only repeat 4 times. That's the logic. You'll get 3 to 4 times when you repeat, you get the numbers. You can also proceed 5 times, but you'll just lengthening the number. Like if you have a precise number like 7.1111, same thing as 7.11 is same as 7.10080 something. So you have to repeat 4 times here, and you have to repeat 4 times here. How do you do this? This logic is simple, clear. Same is this. Thus multiply change the base to 8 in octal. Hexadecimal is a bit crazy. Same thing you need to do. You just need to do divide by 16 everywhere you are just doing it. Divide by 16 everywhere you are doing it. And you'll be getting a 258. Go from bottom to top. 258 you just write for this part. Very easy. Right. But if you need 49 to hexadecimal, same thing. You do this, you get 31. Very easy, right? To understand this, then 0.675 to hexadecimal fractional part. But so here I can see 10.800, 10 you remain, this into the 12.800. 800 is repeating many times. So let's stop there, and 12, and you go from bottom to, sorry, top to bottom order here. So 0 point what? 10 is A, 12 is C, 0 point E, C, write it. And this is a number, right? So you have to understand something yourself also, everything I will not explaining. So remember, when converting fractional decimal to hexaoctal, students often end the integer part of the multiplication step in wrong order. Fractional parts are top to bottom, integer part are bottom to top. Fractional top to bottom, decimal part, integer part, bottom to top. You need to do it accordingly. Don't get confused by that. What I'm trying to say here. Then conversion from other number systems to decimal. That is like we need to convert binary, octal, hexadecimal to decimal. What is the rule? Multiply each digit by its positional value, base raised to position power, and add all the products. Integer part positive powers, fractional part negative powers. See the thing. Visualize this. You have a number 1011, 01 to decimal. How do you do it? This is a, you start like 0. This is 0 part. There are 6 digits. It is 1, 2, 3, 4, 5. 5 is this part. 0 is this part. Right? Something like this. Okay. To do the straight line, let's say 1 0 1 1 0 1. This is position 0. We have position 5. 4 position, 3 position, 2 position, 1 position. Multiply it according to position with the 2. 2 to the power 5. 0 into 2 to the power 4 plus 1 into 2 to the power 3, 1 into 2 square plus 0 into 2 to the power 1 into 1 into 2 to the power 0. 2 to the, anything to the power 0 is 1, so we don't need it. So, and just we add it. Then you just add these values. What will be getting? Let's say this is 32, this is 0, this is 8, this is 4, 0, do the sum, 45. That is what you get in binary to decimal. In decimal format, from this binary to decimal we get it. Then this is integer part. If some float part, fraction part is there, how do you do it? For the integer part, it still remains the same. This part remain the same, right? From this part, you do 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3. This inverse you do it. 2 cube inverse, 2 square inverse, 2 to the power minus 1, 2 to the power 1 inverse. You do it. And how to do inverse? 2, this is, the math here. You know the math here, you know the math here. So what to do, you know this? Simply add all these things, do this. Right. So do you understand the position value of this number? 110101.010. This is position 0. This is one position, this is 2, this is 4, this is 5. With accordingly we are doing all these things, right? And this is a minus 1. After the dot, minus 2, minus 3. Multiply just with 2 because we are converting from binary to decimal. Multiply this, then add all these things. Done. Then octal to decimal. Same thing. I have a number 156. This is 0 position, this is 1 position, 2 position. I will do 1 into 8 square. Just change the base to 8 from 2 because octal to decimal. And 5 into 8 to the power 1 and 6 into 8 to the power 0. Then you do the multiplication, this part, then add that and you get 110. And so this part, you get it. Then SE in 78.12, you can see here what is happening. That 78.20 provide the logic. This is 101. After the point, it minus 1 minus 2. So I do 7 into 8 to the power 1 plus 8 into 8 to the power 0 plus 1 into 8 to the power minus 1 plus 1 into 8 to the power minus 2. I need to do that's easy. Then just add up all the things and you get this part. Then this part and this part you have to solve in maths, or maybe a calculator might be allowed, or some examination probably easy questions will be coming. So you can do it like by mouth or hand manually. Then hexadecimal to decimal, same thing. I have 0.87. You do it, this is a 0 position, minus 1 position, minus 2 position. You do it 0 into 16 base to the power 0, 8 into 16 to the power minus 1 plus. This is a bit harder because to calculate all these things you need a calculator. So just do this and add up all the things. It is quite easy to do. I don't know what happened now, right? Then you go for 3a5. How to do the same? This is actually 10, you should know. This is 10. A is 10 na? And then write that this is a 2 position, this is 1 position, you have the 0 position. Right? 3 into 16 to the power 2 plus 10 into 16 to the power 1 plus 5 into 16 to the power 0. You do it, add it, get the thing. Hexadecimal to decimal, easy. Just substitute the value. Remember, A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. Always substitute the decimal value of letters before multiplying. This, remember, this is easier in hexadecimal to decimal conversion. Then other 6 types of conversion, that is a direct conversion between binary, octal and hexadecimal. Since we know why direct conversion works, we need to understand it first here. Since 8 is equal to 2 cube and 16 is equal to 2 to the power, for every octal digit is 3 binary bits we can represent. Previously we saw, and every hex digit we can represent 4 binary bits. So we can directly convert it by grouping the bits. No need to go through a decimal point. So there are 4 steps. Let's say from converting from binary to directly to octal without going the decimal wala system. Group binary does in 3 sets, starting from radix point going left for integer part. For the fractional part, group 3 bits from radix point going right. Add leading and trailing zeros to complete the incomplete groups. Remember the rules and replace each 3-bit group which is octal equivalent using the table. Let's say we have to convert. This is in binary, some big number to octal, let's say. How to convert this? How to convert this? Group in part of 3. Group in part of 3. That's the main logic. You 3010 is here. That goes here, right? Then I think 011 is here. Group in 3. Right? 011 is here. Then you have again 011 is here. And 1 is here. We have remaining one. Add some leading zeros to it if it is not getting fulfilled. Then add the position 1 001 in octal is 1, 011 in octal is 3, 011 in octal is 3, 010 in octal is 2. We know that. Then we convert 1 3 3 2 in octal. We know this octal wala thing, right? From the when we learn that table in octal number system, we learn this table now. What is the value here and here? So yeah, to remember that thing only. And yeah, if we have a fraction part, we convert the first, we go for the same thing for the integer part, fraction part. This part is there, you group it. Let's say this part you need to go from right to left, but this part you need to go from left to right grouping. So you group this 0, this part. How do you group this? 0 1 0, then 1 1 is left, add one trailing 0, group this part, group this part in terms of 3. Then and 0 1 0 is a value of 2, and right, and 1 1 0 is 6 as per that octal number table. Then write this 254.26 is a value in octal when you convert binary to octal, basically, right? Then when we convert reverse, it's octal to binary, replace each octal digit with a 3-bit binary equivalent. That's why just remember the table I'm saying. Let's say you have to convert 767 to binary, we need to convert. How do we do? 7 in octal is what? 111. 6 in octal is what? 110. Remember that table. 7 is again 111. You just write 111, 110, 111 here. This becomes easily. If some fraction is there or floated part is there, you can see here. How do we convert it? Integer part remains the same. Write the same part, still this part. And 1 and 5, how do you write it? 1 is 001, write it. 5 is 101, write it. Give a point here, write this part, write this part. It is like this here, right? You can see this part, isn't it? This part, right? Then so that is binary to octal, octal to binary completed. Then binary to hexadecimal. Group in 4 bits starting from radix point, leading trailing rows as native, just add it whenever is required, and replace each 4-bit group with hex symbol within the table. A to F, that is from 10 to 15, you need to convert it. Let's say I have this big number and I have to convert this from binary to hexadecimal. How do you do this? You group this basically. How do you group this? 1101, you do basically from right to left, I'm saying. The 1101 is here. Then afterwards 11110 is here, right? You need to take it carefully considerations. Then 0101 is here, you need to do it. And what you are left is 10. Add two leading zeros and complete this 010, right? And you know this from the table, that is 001 is 2 and 0101 is 5, 1110 is E and 1101 is D. And how do you write it? 25ED, and this is E, this is D in hexadecimal, from binary to hexadecimal. We know this things from the table, right? When you go above in the hexadecimal, we discuss this table. Remember this table is there from 0 to 7, it is there, and from 8 to this part is one part and this part is one part. That's why I tend to remember this part and this part. You need to make conversion, or you need to write it in order the pattern. You need to at least remember how the pattern actually works here. Then if you need to convert some decimal part, right? This is 49, sorry, with some decimal part is there. Let's say this part you will write it from left to right. 0101, you will group this into 1, and remaining is 11. Add two trailing zeros, write this is C, this is 5. Give a point, write this AC, this is AC as usual, point 5C, from binary to hexadecimal conversion done. Then in the reverse, hexadecimal to binary, replace, this is most easiest, replace each hex digit with 4 binary equivalent. 7 be 316, replace 7 with something, B with something, 3 with that hex digit 1 and 6, and write this whole part, add this whole part, and write it in format that is from hexadecimal to binary. If you have fraction, write this, give a point, then again write this part. You know how to do it? Great. Then comes the other two, hexadecimal to octal, octal to hexadecimal. To concentrate here in the here hexadecimal to octal, convert each hex digit into its 4 binary equivalent, regroup all the bits into 3 bits from LSB to MSB for integer part, and replace each 3-bit group with its octal digit. Let's say convert 4B2A to octal. So I have 4B2A. I write this in this format of your the hexadecimal to octal when we are converting. First, we need to convert it into binary form. You group this in 4 forms, write its binary equivalent, group this in 4 parts, then regroup this part into 3-bit groups. Right? So if you clearly see this part, how you can make you see this. Okay, let's have the number visualize this. 0 1 0 is one triplet, you can say. This part chopped up, then write 101 is one triplet chopped up, that is 101 here, right? Then is 100 is one triplet you chopped up, just group this part. 101 is one triplet, write it 101 you got here. 100 you got, chop up this triplet. 0 is only left here to add some leading zeros to it to make it 000 automatically. Then you, after you regroup this into 3 bits, you try to convert this whole thing into its octal equivalents, into its octal equivalent. So here grouping is done. 0 in octal equivalent from that octal number system table. 100 is 4, 101 is 5, 100 is 4, 105, 1010 is 2. So from this hexadecimal to octal, how will you convert it? You will replace this in the binary, then from then you convert it into octal, right? That is the whole process. You can remove this 0 as the leading zeros, you can just remove it and write it like this. So that's completely correct, no problem. Same thing you also need to give when we are going from octal to hexadecimal. You have to convert it a binary equivalent, 3-bit binary equivalent, regroup all the bits into 4-bit groups and replace each 4-bit groups with a hexadecimal symbol. Let's say we are converting this part, very small number 765. You write the 765 in terms of a binary equivalent, right? 3 groups, then combine this whole thing, combining 111 for 7 I have, 110 for 6 I have, 101, then regroup into hexadecimal as we are converting to hexadecimal. So this is 0101 is one part, 1111 is one part, one is remaining, are 3 leading zeros. To write 001 111 and 011. So like this you convert it in from the table that we give at hexadecimal 1, and this as f, and 0101 is 5. Write it 1 f5 when you convert it from octal to hexadecimal through binary format. This thing, so you have to again, like you have to remember this from the table only, which I gave you. Take a note of that table actually. Is octal and this table for hexadecimal, and this table for octal. 0 to 7, here it is the same 0 to 7, this has 0, and here it is 8 to 15, then and you represent is A to F format. Just remember that conversions you have to do like this. So all the 12 type of conversions are completed here, and the memory trick is what? BOS triangle, binary as a center to go octal group in threes, to hexadecimal group in fours, to go between octal and hex, always pass the binary as a bridge between them. Expand the binary, then regroup it. That is the conversion pathways. Then we proceed ahead to the next part of this chapter. Number system is over as of here. Then we come to encoding schemes. So what is encoding basically? Encoding the process of converting data or characters or symbols from one form, let's say human readable form, to other is a machine readable binary form. Since computers only understand binary, every character on the keyboard must be mapped to a unique binary code, right? So first, our system is our ASCII. Remember this full form or abbreviation. It is often asked in exams. What is the full form ASCII? American Standard Code for Information Interchange. It developed in the early 1960s by the American Standards Organization in the United States and uses 7 bits for encoding. So we can represent it in 2 to the power n. It means how many characters? 2 to the power n is 128 characters we can represent it. So remember how many characters it is used in this part. Very important. So it has a total of 128 characters and it 2 to the power 7 and 7 bits for encoding as it uses. Right. Of 128 digits, 95 are printable. That is a digit 0 to 9, letter A to Z or uppercase, lowercase, some punctuation marks. Other control characters or the white space characters are the new line, tab, backspace are there. Right. Only encodes English language. And ASCII is a superset basis for Unicode. Later we'll see what is that. So the ASCII value for space is 32, uppercase is 65, and A to Z, if you go like this, A to Z uppercase 65 plus you do 25, rest 25, there's 26 alphabet, A is already counted, baki bacha of the 25, the Z is probably 90. This is a binary 7 binary format. Like that, lowercase a is what? 97. Lowercase z is plus 25 will do. So we'll get it as 122. The b जो होगा it will be lowercase b is 98. It's just plus 1 incrementing. Just in uppercase same, lowercase same. Space is 32. Then 0 to 9 how will represent? 0 to 9. 0 is 48. 9 is plus 9 you do, that will do 57, and 1 is 49 respectively, plus 1 you are going. So remember this and take a screenshot of this if required. So if there is a question, encode data in ASCII value, how will do it? A you know is 65, D is how much? Plus 3 you do 68, T is like 84, A is again 65. Write the 7-bit binary equivalent for that. So D is something, A is something, T is something, A is something, right? You know how to write the binary equivalent. Probably binary equivalent is basically, remember, of a is what, how to write the binary equivalent. Okay, this is it is not really asked how to encode this and that, but it's an example. If you can remember the binary equivalent, or maybe there's a logic, but it's not there in this syllabus as far as now. And there is a ISCII, that is the Indian Script Code for Information Interchange. Remember the full form again. Developed in the mid 1980s by the Bureau of Indian Standards (BIS), and an extended version of ASCII that is using 8 bits. So you represent 2 to the power 8 or 256 characters, double the 128 characters of your ASCII. It supports ASCII plus Indian languages are there. The additional 128 retains all the 128 ASCII codes of the same thing of English language, and the additional 128 codes are of Indian languages. Therefore, the extras are syllables of Indian language. Like your, these are the scripts that is there of different Indian language. Devanagari script is there, right? If we use this, other languages are there. The ISCII were designed specifically to bridge the gap between ASCII and the needs to encode Indian languages on the computers. Then is a Unicode, or the Universal Character Encoding Standard, developed and maintained by the Unicode Consortium and non-profit organization members. Big companies are there here, big tech companies, and those members are there. Provides a unique code point to every character in every language of the world. Code points are independent of your, they are machine independent, means CPU architecture independent, software independent, operating system independent, and currently covers 161 scripts and a superset of the ASCII. Unicode defines two mapping methods: Unicode transformation format, other is a universal code character set. In the syllabus, UTF-8 and UTF-32 variant is only there. That is Unicode transformation format. This UCS we don't have, universal code character set. So this, what is UTF-8 basically? Bit used is UTF-8 is 8, 16, 24, 32 bits code point. Variable which is 1 to 4 bytes it can take. Mostly used on the internet, backward compatible with ASCII is a feature. UTF-16 is not there in the syllabus, but still we will be learning this. 16 or 32 bits per code point. Variable which is 2 or 4 bytes and used in Windows operating system Java internally. UTF-38 is 32 bits per code point. Fixed which is of 4 bytes. Simplest way is a small memory. Every character equal to 4 bytes. Take this screenshot of this. It's important. तो when real life example जैसे हिंदी में हम लिखते हैं आ लिखते हैं maps to hexadecimal code point 0905 with binary equivalent is something and the Unicode table for Devanagari starts at this. Okay, sometimes in question, not in board exam, but in school exam, there's no board exam probably in 11. So UTF, why this UTF-8 uses more space than UTF-8? 32 uses more space than UTF-8. 32 uses a fixed 4 bytes, means 2 to the power 4. 32 bits for every single character it takes. Even a simple A which only needs 7 bits in ASCII gets 32 bits here. UTF-8 uses only 1 byte, that is 8 bits for standard ASCII characters and expands only for complex scripts when it is needed. That is why UTF-32 is far more memory intensive than UTF-8. So remember this, sometimes this is asked one important question here. And this is a whole comparison table for your reference. You will read it. So yeah, what we discussed today? We discussed the number system, binary, octal, hexadecimal, decimal, the bases, two to the power and formula again, conversion rules from decimal to others, others to decimal, fraction to others and fraction to decimal how it is, shortcut conversions of the 12 number systems, right? We need to remember that. And encoding schemes of ASCII, ISCII, Unicode, UTF-8, UTF-32 in particular, and how it is memory intensive. 32 is greater than 8, you need to remember. Some common mistakes you need for students make. Reading binary division, how you proceed it. From bottom to top, sorry, top to bottom instead of bottom to top. Fractional multiplication, bottom to top instead of top to bottom. That rule. And how to do from left to right, the right to left, that what I taught. Remember this. Sometimes leading and trailing, padding zeros. What is MSB, LSB? Conversion steps. Hex to octal you must go through binary. Octal to hex you must go through binary as an intermediate step. Then regroup this. Don't confuse ASCII with ASCII 2 to the power 7 and 2 to the power 8. 128 and 256 respectively. And these are the most important things for board exams, even not board but school exams. On this chapter you can see this. And what is the application of hexadecimal? That is can be asked sometimes. Memory addresses, web color, MAC addresses, remember in short. Full forms, conversion, fractional parts especially is there. But that's most of the thing. You want to see this chapter summary here. We have okay. Some practice questions are for your reference. You can take screenshots of them. Right. Some random questions are here. You want to take screenshots, just see this and quickly just take it. Important questions. Okay, that's all. So yeah, chapter 3, unit 1, 3 chapters completed, 10 marks done of class 11 to class 11 syllabus computer science, right? So we completed this thing and congrats for completing 3 units till date. And that's all. Later we'll be uploading the introduction to problem solving on the unit 2 first chapter there. Very easy chapter it will be. Introduction video will be coming next ahead. So stay awaited for that. And the notes for this will be given in the description and maybe probably in the description also in the comments might be. Yeah. So anything else if you need question and answers, important things, other stuffs, mind maps. Mind maps will be in the notes probably. There's a visual map will be added to it. Right. The other things what you need just write in the comments. Do like the video and subscribe the channel. So that's all, and thank you and bye bye, take care.